This is Jack Jackson. In this video we're going to talk about how to approximate the derivative at a point given a graph of a function. So for example, here we have a graph of a function g of x. And suppose we want to approximate, let's say, g prime at 1. Now let's think about it. How should we go about doing this? Well, we've already remembered how to approximate from a table. Let's review that real fast. So if we have a function given by a table and we want to find f prime at 4, we just did a symmetric difference quotient by going either side and using the slope formula. Like that. Now, we can do the same thing here. Now in theory, one could actually try to take this and say, take here and try to draw the tangent line here, maybe take a ruler or something, and measure the slope of that line. In practice, that doesn't work very well because it's so easy to miss the slope by just a little bit, and you can be pretty far off. But we can use this technique of the symmetric difference quotient pretty well. So what we need to do is find 2 points on either side. Now, we might do this, in theory you should be able to do it from 2 points very close, but again, as you get too close, sometimes it's hard to estimate, and estimating those fine of a differences are a little bit problematic. So in this case, it's going to work out pretty nicely if we'll just go from this point to this point here on the curve. So if you look at that, here we have delta x, and we know that delta x, if we go from grid line, is exactly 1.2 minus 0.8, or 0.4. What we have to estimate is this delta y. Now you can do it this way by drawing it and estimating here, or I'm going to estimate it by trying to find the coordinates of those points. Let me get my marks out of the way so you can see a little bit better. And we need to estimate what those points, what the coordinates of those 2 points would be, right there and right there. So when x is 1.2, what's y? Well, we need to look at our scale. So notice that the scale going horizontally goes up by 0.2 each, but goes up by 1 each here, and your axis is down here. So this first line is 1, that's 2, this line up here is 3, so it's 2 point something. To me it looks just a teeny bit over half, so I'm going to call that 2.6. So I'm going to call this the point 1.2, 2.6. And this point is 0.8 exactly for the x, but what's the y? Approximately, well, let's see, that's 1, that's 2. We're up close to 1.8 or 1.9. I think it's about 1.8. Now, of course, there's some estimation of approximation going in there. So delta y is 2.6 minus 1.8. That's 0.8. And of course then the slope is delta y over delta x. That's 0.8 over 0.4, which is 2. And of course the f prime at 1 is approximately the same as the slope of that, which is approximately this. So we get 2 for the derivative. Okay, I'm going to erase this. Okay, as we move down here, you'll see in my notes that I have this worked out. I think I have it worked out the same way. There we go. Same thing there. 2.6 minus 1.8. Okay, let's try another one. This time you do it. G prime at 2. Okay, so let's go back. Whoa. Let's go back to here. And let me zoom in a bit, maybe make it a little bit easier for you to see. Yeah, that's not bad. There we go, we zoomed in even more. Okay, look at that zoomed in picture. You tell me what G prime at 2 would be, or at least approximately what it is. Use the same technique we just did, and go ahead and figure it out yourself and come back and we'll check it in a minute. Press pause now. Okay, now if you're back, you can see that we're looking here at the graph. We want to, here's our point of interest at 2, so we want to go a little bit to the left and right, say from this point right here to this one down here. Okay, so delta x is again 0.4, 2.2 minus 0.8, 1.8. What is delta y? Well, let's see, we need these y values. Now if we start with the right and go back to the left, so we need to find this one first. Let's see, that's -1, -2, -3 is here, -2 point something. Let me erase that and get it out of the way. Okay, what is that? -1, -2.6, -2.7, something like that. And then this one is 1.1, 1.2 maybe. And so that's -3.8. So -3.8 over this is, remember this is 0.4. That's the slope, delta y over delta x. And so we can work that out. That's 0.9. 5. Okay, I may have worked it out a little bit differently down here. Oh, it is negative. -9.5. Yeah, -9.5. Okay, and that's what I have worked out here. Now, of course, there's some room for error here. There's definitely room for error because in 2 places, well, 3 places, we're making estimates. The first place we're making an estimate is we're making an estimate because we're estimating the slope by finding the slope of this secant line going across here rather than the slope of the tangent line here. But of course, those should be pretty close to the same. Then we're also making estimations because we're estimating, we sort of picked delta x, so we kind of knew where that was, but we're estimating this length of delta y, or in other words, estimating these 2 distances here and here for the y values of those 2 points. So we're definitely making some approximations, making our best guess by looking at the picture. Okay, and so that will make us some room for error. Okay, let's try another one. Okay, look at this graph here. Oh, one more exercise before we do that. Let's back up. Okay, look at this graph here. Tell me what the sign is of the derivative. Okay, is the derivative positive or negative or 0? Well, if you're in here, notice that you're talking about a slope going like of a tangent line, something like that. Well, that has a negative slope. In here, still a negative slope. Negative slope here. Here's a negative slope. Right here at the bottom, the tangent line is horizontal, so that's a slope of 0. So this is negative. Right there, the slope is 0. Here, the slopes are, what are they? Positive slopes. Right there at the top, horizontal tangent line, so slope of 0. And over here, the slopes are all going this way, so these are negative slopes. So remember, in general, that when the function is increasing, okay, so for this part of the graph, I'll trace over it in blue. So from here up to here, we have positive slopes. And I'll trace over in red the other part. This part of the graph here and this part right here has negative slopes. So for any x's where the graph is in the red portion, the derivative is negative, the function is decreasing, and where the derivative is positive, the blue part of the graph, the function is increasing. At the points, right at the points here where right at that maximum and that minimum, those are places what we call stationary points. The derivative is 0. So at least in talking about instantaneous rate of change there, it is actually 0. We call those stationary points. Okay, right there and right there, the slope equal the derivative equals 0. Now notice in a way this doesn't make sense with pre-calculus, because in pre-calculus, remember, you had to have 2 points to talk about a slope. But here we're talking about the slope at a single point, namely the slope of the tangent line, which is the derivative. Okay. Now, notice that where we had stationary points, one possibility for a stationary point is a local extremum. So right there at the highest point, that guy right there is a local maximum, sometimes called a relative maximum. And this one right here, also slope of 0, is a local minimum, or a relative. Two different words for the same thing, minimum. So, if you draw a circle around it, it's the lowest point in that circle. You know, Mr. Minimum's neighborhood, he is the lowest one. This is called a neighborhood. And so in this neighborhood, we have the highest point. Now notice this one doesn't really have a maximum because this goes up forever, and this continues down forever. So it has no global minimum or global maximum, or if you use the word local here, you'd use the word global for overall maximum or minimum. And relative means locally, and instead of relative, if you talked about an overall maximum, it would be called an absolute maximum. So this one doesn't have an absolute maximum or minimum. If you don't care whether it's a maximum or a minimum, it's called an extremum. And of course the plural is extrema. Plural of maximum is maxima. Plural of minimum is minima. So these are plural. Maxima, minima, extrema. Singular, minima, extremum, maximum, minimum. Okay, I think I got another example here for you to try yourself on finding an actual value here. Let's see. Here we go. Look at this graph right here. Okay, it's coming along here along the asymptote on the x-axis, then it goes up like maybe an exponential function. Estimate f prime at 4. So approximate f prime at 4. Go ahead and do that yourself and come back. Press pause now. Well, now that you're back, again, we want to go on either side, but we could go one grid line. Wouldn't be too bad. We could go at this point here and this one here. But I'm going to try to go about halfway in between two grid lines and pick my points to be there and about there. So if you drew a vertical line right here in the middle of this grid line, in the middle of this grid line here, looks like those are your 2 points. Now in this particular scale, looks like it's 1 each horizontally, 1 each vertically for the grid lines. So that's actually a delta x is 1. And so actually, since delta x is 1, let's try that again, then this vertical distance here, here's the horizontal distance, but this vertical one is actually the derivative. We can just figure out how big that is. Again, we can do it we can estimate that by estimating the coordinates of those points. So again, we're looking at a point right about there and right about there. Okay, so what is delta y? Well, we just need to find the two y values. Okay, and I said this guy is about 1.8, and I said the y value here is about 0.5 for a delta y of 1.3. Okay, and then of course the delta x is 1, so 1.3 is our estimation or approximation of the derivative. I actually know the formula for this one and know a shortcut or an alternative way of doing this to actually compute the actual limit, and it turns out to be, to 2 decimal places, about 1.24. So 1.3 actually was a pretty good estimation. Okay, let's look at this. Let's take this and rank this. Now, there's something important missing on this graph. We need to have a scale. So let's let this every other line be 1. So we need 1, 2, 3, 4, 5. Like this. This is absolutely necessary that you need this scale. It was just left out of this picture, so I need to redo this graph and make sure that this is in there. Some of the graph, of course, is off the screen. It probably looks like it comes up here and has a max and comes back down. So we have this graph. So let's first look at these things and see if we can just come up with whether it's positive, negative, 0. So at negative 7, we're right here. We're looking at that slope. That looks like a negative slope to me. Decreasing function. Here at 4, it's also decreasing. Negative. At negative 4, the function is increasing, so that's a positive slope. At 8, we're right here. That one is also a positive slope. And at negative 9.5, we are right in here. That's also a positive slope. So certainly positives are bigger than 0, and negatives are less than 0. So let's look at the positives first. We're comparing the sizes of the slopes here, here, and here. Remember, if you start with something that's a slope of 0, that's a horizontal line, and the steeper you make it, the bigger the slope is. In other words, if you go to the right one, how much do you go up? Well, go to the right a half here, right one and up some. That tells you about what the slope is there. If I get my tangent line right, that would be the slope, this much. Whereas this one, when I go to the right one, we've changed by this much. And this one, when I go to the right one, oh my, it's a whole bunch. It's way up here. Way up here. So which one is bigger? Definitely this one over here is the steepest. So f prime at negative 9.5 is actually the biggest. Now, of these two, the next biggest would be this one at negative 4. And the smaller one then is f prime at 4. Not 4. 8. Now all of those are positive, so they're bigger than the negatives. Now let's look at the two negative ones here. That's here and here at negative 7 and at 4. Well, certainly this one is steeper than this one. But if I'll just get a really rough estimate. If I go the right one, how far down would this go? Well, way down there, right? Maybe negative, I don't know how much. Maybe negative 7 or something. Whereas this one, if I go to the right one, I'm going down, probably less than 1. Okay? So this is around negative 1. This one says around negative 8 or something. Okay? Well, negative 8 is less than negative 1. So notice that a steeper line is going to actually have a smaller slope. So steepness is the absolute value of the slope. And so that's the order right there. So that was, let's just take it to 7, excuse me. So this was A, B, D, C, E is the order. Alright, we'll come back in our next video and talk about how we can approximate the derivative if we have a formula instead.